In this video we use a Navier Stokes equation to model a Couette flow between two parallel plates. Here's the Navier Stokes equation. I like to write it in this form using these dummy variables, as it means you just write one equation out instead of writing all three for each component in the x1, x2 and x3 directions. The Navier Stokes equation is used to define fluid flow in pretty much all cases, from the blood flowing on our veins to flow around a race car, the air flowing around the planet. There are several parts to the Navier Stokes equation, and in most cases it is very difficult to solve, and computers are used, mainly CFD packages, as you can get some quite tricky second order partial differential equations. There are a few cases where these can be solved by hand, and one of them is the Couette flow. So in the first video we're going to be finding the general solution to this Navier Stokes Couette flow problem. So in order to solve this problem, we'd first define draw a picture. Drawing pictures always help in engineering. They break down a complex problem into a much simpler. So here we have the lower plate, which is stationary, and here we've got an upper plate which is moving at some velocity, and we'll call that velocity U plate. Now, in all engineering it's important to state the assumptions, as assumptions allow you to simplify the problem, and in most cases the assumptions are negligible to the final answer. So the assumptions we'll make is the no slip condition, which means the fluid is stationary at surfaces. So with respect to the velocity of this surface, the fluid velocity will be 0, and same with this one here, with respect to this surface the velocity would be 0. As this plate's moving, the fluid will be 0 at the plate, so the velocity at this plate here of the fluid is equal to UP. Other assumptions we'll state is that the flow is just flowing due to this plate moving. There's no pressure differences at either end of the flow. We'll also assume the flow is laminar and steady, and also this system here is aligned to gravity, aligned perpendicular to gravity, so the gravity would be acting in that direction there. Now we can go ahead and simplify our Navier Stokes equation. As we set it steady, this term here goes to 0. Now as the flow is flowing in this direction here, we will I'll just draw the velocity profile. Another thing it's important to when doing these problems is to just roughly estimate what the velocity profile would be. Now we can estimate it to be like this, again from the no slip condition. Now, in reality, this flow could be a parabola, or it could be linear, or any other curves. Now, as it's flowing laminar throughout the current flow, there's no velocity going in the x2 direction on the defined coordinate axis. It's just flowing in the x1 direction. So this here goes to 0. We defined no adverse pressure, so it goes to 0, and also no gravity. So all we're left with is 0 is equal to this term here, and this term here is the viscosity term. Now, it's important to note that you can't multiply these two together, and that's because there's actually 3 parts to this expression. If you multiply these two together to get the partial derivative of xj squared, you miss out one of the terms, so we'll leave it as that for now. Now, as the flow is flowing in this direction only, we want to look at how this flow changes in the x1 direction with respect to the x2. So this term here becomes 0 partial derivative of velocity in the u1 direction and it's been changing the x2 direction. Now, this stage here we can multiply these two together because the flow is only changing in one direction. If this was not the case, say if it was the x3 directions coming out the page, and there's also a term changing the x3 direction, you'd have to write a second one of these here out. That's just a two-dimensional case. This here holds. So then this here is equal to that's perfectly okay to go from this stage to stage. Now, we can assume these partial derivatives are the same as ordinary derivatives. That's just a two-dimensional case. It only depends on one parameter. So 0 is equal to and if we integrate it, we not forgetting the constants, we get a constant is equal to the derivative of u1 derivative of x2, and if we integrate again, So the velocity u1 with respect to x2 now we need to apply our boundary conditions and again come from the no slip. The boundary conditions are at x2 is equal to 0, the velocity is 0. So u1 0 is equal to 0. Plugging this into this equation here, we get 0 is equal to c2 plus c1 times 0 divided by viscosity is equal to 0, so this is 0, so that means C2 is equal to 0. Just for people who are not aware, this sign here means implies. Now our second boundary condition is that x2 is equal to h. The velocity is equal to the velocity of the plate. So we'll write u1 h is equal to u plate. So again, plugging this condition here into this equation, we get u plate is equal to 1 over viscosity C1 H, and we already said C2 is 0, so we can just ignore that in this when plugging this condition into that equation. So that implies that C1 is equal to velocity of the plate times viscosity over H. Now then, we found these constants of integration. In quite a few engineering problems, finding these constants is the challenging part. So now we can write the general solution of the problem. So that is plugging these values for the constants into this equation. So the velocity in the u1 direction with respect to the x2 is equal to 1 over the viscosity times the velocity of the plate times the viscosity over h x2. So basically what I've done is I've brought this 1 over v to the front. So we can see that these two terms here cancel out, and we're left with velocity of the plate times the distance from this edge here upwards divided by the total height of the plate between the two plates, and that's our final expression. This here can be applied to other problems as well quite easily. So if we had a gravity term, say this plate wasn't aligned to gravity, you could apply the same principle. If there was pressure driven flow, you could apply that same principle. A bit more challenging, but can be done. Also, one last thing is that from this equation here, we can see that our original guess of linear profile was correct, as this is a linear equation. If there was an adverse pressure, you would find that this here wouldn't be linear, and maybe a slight curve depending on how complex the problem is.